we leave people and think another topic besides that. So, welcome, Thomas.
Yes, so thank you very much for that introduction. Which I suppose was an indirect way of saying this may or may not be relevant to things you're thinking about, but hopefully it will be interesting in any case. This is joint work with Jamie Robbins at the Harvard School of Public Health. And to give you, let's see, it's not good. Maybe I should use your one. One second. Oh, I see the problem. Okay. To give you a quick overview of what I'm going to talk about, I'm going to describe two different approaches to formulating a causal model. So there's one approach based on potential outcomes that has been advanced within statistics and within biostatistics, often referred to as sometimes referred to as the Rubin causal model. And there's a second approach based on graphs that has sort of come out of work within computer science and has been advanced by a number of people, including Judea Pearl. And within epidemiology, for example, both approaches are used. But how exactly these two approaches relate is something that is not always clear to everybody. And in fact, I think in certain respects, it's something which could do with a little more clarification. And so I'm going to present a unification of these two different approaches. And I'll describe the way this approach works, mainly with simple examples. And I'll contrast it with a previous unification that was proposed by Pearl that I think has some, it is slightly more complicated, that works via non-parametric structural equation models with independent errors. To get started, here's David Hume. And when he was asked to define a cause, he said, we may define a cause to be an object followed by another, and where all the objects similar to the first are followed by objects similar to the second. So sort of in 18th century language, he's saying that if there's a cause, we have some kind of association. But it doesn't take you very long to realize you could easily have a context where you have some association without us wanting to say the relationship is causal. So you can imagine two grandfather clocks, one of which is 1 second behind the other, and the first grandfather clock chimes, and then 1 second later the next grandfather clock chimes, but we don't want to say that relationship is causal. And so Hume adds in this extra little caveat where he says, where if the first object had not been, the second never had existed. And so notice, whereas here he's talking about things that are directly observed, here he's talking about what would have been seen under other circumstances. So he's basically saying, if we take a sledgehammer and smash the first grandfather clock just before it strikes, the second grandfather clock will continue to strike. And so that's the reason why that doesn't count as a counterexample to his characterization here. So I do add that here for anybody who sort of follows philosophy of science, Hume is famous for 3 different causal theories. This is not one of them, but it's the one I'm going to develop. So professional philosophers say this was just a throwaway comment of his and we shouldn't dwell on it. It's a very valuable throwaway comment, I think. So jumping forwards to the 1920s, Neyman, in his master's thesis, is looking at the analysis of crop trials, and he says basically that if we want to consider V varieties of crop on M plots, or it could be fertilizers, we'll consider a set of numbers. It explicitly says we're going to think about a set of numbers like this, where we have 1 column for every plot and 1 row for every variety. And the key point is that we can only plant in any given plot. We can only plant 1 variety. So this table of numbers represents what would be observed if we did experiments other than the one that we actually did. Okay? So we're only going to be able to plant 1 variety in each plot. which means that we are only going to get to see one number in each row. Because if we decide to plant variety 1 in plot 1, then we are going to not be able to see the results of planting any of the other varieties. So we only get to see one number per column. So now, sort of simplifying to keep the presentation as simple as possible, let's now just go to the very simple case where we have a binary treatment. So in terms of the previous slide, we have only two varieties or two treatments, and let's also suppose that we have a binary response. So then we can talk about y of x equals 0, the value of y that would be observed for a given unit if assigned to x equals 0, and y of x equals 1, the value of y that would be observed for a given unit if assigned x equals 1. So conceptually, for every individual in our study, we're going to think about there existing these two different numbers corresponding to what would be observed under these two different treatments. Okay? And a little bit of notation, I'm going to, because these equal signs clutter things up, I'm going to write this like this often, just as a shorthand. Okay? And implicit here, you might think, well, I haven't assumed anything yet, but implicitly I'm supposing that these things are well defined. So I'm supposing that, say, whether or not my outcome only depends on whether or not I'm assigned treatment and not on whether or not other people are assigned treatment. So we're supposing that, say, this is not a treatment for an infectious disease. It's not something like a vaccine where my outcome might depend on who else is vaccinated. Or, to say it another way, if we are supposing so people sometimes do apply potential outcomes models, but in those cases they suppose that the individuals they're observing are sufficiently far apart and the time scale is sufficiently short that it makes sense to think of these potential outcomes as well defined. So that's often called no interference or the stable unit treatment value assumption. So how many of you have heard of potential outcomes before? I want to judge how much. Those of you that are in my class should have heard them. But okay, so I'll continue with a little bit of review here. So this is the picture we're imagining. These are this is our full data. We never actually get to see this. This is sort of the God's eye picture, but this is telling us not just the results of the experiment we did do, but also the results that would be observed had we exposed patients to the other treatment as well. We can distinguish between, we can think conceptually about different types of patient. So a patient who has, I'm thinking of 1 as a good outcome here, a patient who has zeros in both columns is of type never recover. It doesn't matter whether we give them the drug or the control. Their outcome is bad under either setting. We can contrast that to a patient like this, where if they're given the control, they have a bad outcome. If they're given treatment, they have a good outcome. This is the converse, and this is somebody who always recovers, who always has a good outcome regardless of what we assign them. Okay, and then the way that our potential outcomes are related to our observed data is as follows. So supposing that each patient is assigned, we're not making any assumptions at the moment about how they're assigned. It could be that they're choosing treatment, their doctor could be choosing treatment, they could be flipping a coin, who knows. Somehow they end up either getting treatment or control. Then, sort of in the sort of obvious way you would imagine, we then, our observed data then is simply copied from the particular column of potential outcomes in the obvious way. So this first guy was assigned to x equals 1, so his observed y outcome is this one here. The second guy is assigned to 0, so the observed outcome is copied from here, and so on. Okay. So this is, in fact, all that we get to see. So that in reality, we don't know what are the we don't know the entries where the question marks are. So for this first person, we know that we know that they were assigned to treatment and they had a good outcome. So we know that they might be helped, but they might also be always recover because we don't get to know what's under that question mark. And so the fundamental, what's often called the fundamental problem of causal inference that we face, is that we that we only get to see one out of each of these two outcomes. So the kind of quantity that we might be interested in, one quantity we might be interested in, a sort of very basic one would be the average causal effect of x on y, which in this simple setting. So it's the difference in expectation between everyone getting treated, the average outcome if everyone were treated, and the average outcome if everyone were given the control. And with a simple binary outcome of the type we've seen here, this corresponds to the difference between the proportion of people in our population who are helped and the proportion who are hurt. Okay. So from a policy perspective, this is a quantity of interest because it's telling us about the effect of treating everybody versus treating nobody. Okay. So it should also be mentioned that the fact that if this is 0, it doesn't necessarily mean that the drug is not doing anything or the treatment is not doing anything. It could be that some people are helped and some people are hurt, but they have to exactly balance out. Okay, so if x is assigned randomly, then we'll get these independencies. So x will be independent of the potential outcome under control, and x will be independent of the potential outcome under treatment. And then it then follows that we can then identify this quantity. So even though this quantity, sort of when you first hear about it, it sounds as if, how could I possibly learn that? Because this is the difference between the average when everyone gets treatment and the average when everyone gets control. We can identify it under randomization because the fact that x is independent of these potential outcomes means that this is equal to this, and this is equal to this. And then this quantity we actually get to observe, because this is talking about the average outcome under treatment among people that actually got treatment, which is just the same as the average outcome that we see in the treatment group. And this will be, likewise, this will be the same as the average outcome in the control group. Okay. So the basic point is, under this particular independence, these two independencies that we have up here, this quantity is identified from the observed data. Okay. I just want to contrast that for a second, just as a sort of little aside. We could think about what we can do in the case where we don't know. Supposing that we don't know that treatment wasn't randomized, and we can't safely assume that x is independent of the potential outcomes. So we could play the mind game of thinking about a set of data like this as if we were a lawyer. So suppose that we had, I just give you this set of data, and I say to you, now suppose that you're trying to argue for the treatment. You're trying to make the best possible case for the treatment. What's the largest number of people who could be helped here? Okay, so if we look at this, and we can see, so these people here, they got the control, and then they had a good outcome. So obviously they're not helped. The people here, likewise, they got the drug and they died. So obviously we can't pretend that they're helped. There's nothing we can do about them. But the people down here who got the drug and had a good outcome, if we're a bit the lawyer if we're trying to argue in favor of the treatment, we're going to say all of those guys are helped. And we're also going to say that all of those people are helped. And say all those people that got the placebo and then had a bad outcome, if only they'd had the drug, they'd have had a good outcome. So we're going to claim that all of these people and all of these people are of type helped. Okay, so we're going to claim that 600 out of our 2,000 are of type helped. What about the smallest number of people who could be hurt? Okay, and if I'm a lawyer for the drug company, do we have to admit that anyone was hurt? Do we have to admit that anyone was hurt? So think about it. You've got, okay, so somebody comes along and says, well, here are all these guys that took the drug and they had a bad outcome. What's the lawyer going to say? Of course they had a bad outcome. These people were just completely, were obviously very unhealthy, and they were going to have a bad outcome no matter what happened. There was nothing we could do about them. Okay? So we're just going to claim that all of those people are of type never recover. And these people down here, these 800 people who didn't get the drug and had a good outcome, we're just going to claim that all of them are indestructible, but even though they didn't get our fancy drug, they would have lived regardless. Okay? So we're going to say that there's nobody who is of type hurt. Right? And so our maximum value of the ACE that we'll see will just be 0.3. this, we've got 30% of the people of type helped, nobody of type hurt, so a maximum value of the AC is 0.3. Similar logic the other way around. If we were now arguing against the drug, we're going to claim that nobody was of type helped, and we'll claim that these people were all of type hurt, and we'll get a negative value for the minimum value of the AE. So sort of key point here is that we can get, even though we haven't made any assumptions, we can infer something about the average causal effect. So that's the good news. The bad news is, if we think about it for a second, we can see that our bounds are always going to contain 0, so that we're never going to be able to conclusively argue that it does or doesn't have a particular effect.
So why, I'm a little confused about the meaning of X is your treatment and Y is your result, right?
Yes, observed result, yep.
So it's like 0 is died and 1 is survived?
So y equals 0 is a bad outcome, and y equals 1 is a good outcome, yes.
Y equals 1 is the good outcome. So then the good is always on the bottom, the bad is on the, because you were saying it's a moment. Okay, all right.
You follow?
Now I'm
Okay. So basically, if we don't have this independence, we can get bounds on the average causal effect, but those bounds always straddle 0, which is unfortunate. Yes. So in essence, some kind of randomization is going to be essential for, we might not have to have randomized. There might be situations where we can act as if things have been given sufficient covariates. We might believe that this holds approximately conditional on other covariates, but we need some independence in order to draw non-trivial causal inferences. So here's the summary of the counterfactual approach. For each unit, there's one outcome that will be actual and the others will be counterfactual. So what we've done is we've reduced causation to missing data, which I think is conceptual progress. Causation is something that many people get excited about. Missing data is something that statisticians get excited about, but not so many other people get excited about. We've seen that the average causal effect is identified if we have this independence holding. Randomization of treatment would assure this, but it might happen without randomization. And the ideas that I've shown you here are central to Fisher's exact tests and many parts of experimental design. And this framework is used in many practical causal data analyses in biostatistics, econometrics, and epidemiology. OK, so that's the quick review of potential outcomes, which is one approach to formulating a causal model. I'm now going to describe a second approach based on directed graphs. And this approach originates from ideas in computer science. And in some sense, it's slightly different in that the type of situations that are considered tend to be more, it extends better to multivariate settings. I think it's a fair comment to say that. And it starts off by thinking about conditional independence and factorization in joint distributions. So the starting point is that we write down a directed acyclic graph like this, which computer scientists know as a Bayesian network. And we associate with that, this graph, a factorization of a joint distribution where for each vertex in the graph, we have a random variable. Okay? So the factorization is very intuitive. Simply say that we have one term in our factorization for each vertex in the graph, and that we simply have a conditional density for that variable conditioned on its parents in the graph, which are those nodes pointing into the given vertex. So in this example, A has no parents, so we just get the marginal density of A. Then we get B given A, C given A, D given B and C, and E given D. So now I should ask, so how many of you have come across this kind of graphical model or Bayesian network before? OK, so some of you have come across it as well. OK, good. OK, so this looks very causal, right? It's very suggestive. In fact, it's so suggestive that at one point in time, Microsoft had a database product that had sort of data mining tools that were built in. And one of the data mining tools would take your database and then would try to extract the structure of a graph that described your database, and they had to drop it because people complained because the graphs that would come out would sometimes involve edges pointing backwards in time. And so they said, how could this clearly there's a bug, this clearly isn't working. The point is, of course, that there's no, if there are omitted variables in if you didn't manage to remember to measure everything relevant in your database, there could perfectly well be hidden variables. And if there are hidden variables, then there's no reason why if you ask the computer to find a structure which doesn't include any hidden variables, then it may be forced to do strange things like have arrows pointing backwards in time. Anyway, the basic point here is that there's nothing causal here yet. These edges are suggestive, but there's nothing causal here. I should also add, there's a graphical rule, and this is going to be important, but I don't have time to define this for you if you've never seen it before. There's a graphical rule which means that given the graph, given any distribution which factors according to this graph, you can read off conditional independencies. So you can read off from the graph, by the absence of a certain kind of path, you can tell that if there's no path of a certain form, then a certain conditional independence will hold amongst the variables in the graph for every distribution that factors according in this particular way. So here, for most examples I'm going to give, it will be somewhat intuitive. So for example, E is independent of A, B, and C given D. C is independent of B given A, and so on. So, so when these graphs are interpreted causally, there's a convention that's given. And the convention is that, that you have to include any potential confounders or hidden variables, and that the convention is if I draw a graph such as the one on the left, then by convention I am asserting, if I'm now trying to interpret this graph causally, I'm asserting that there is no variable like this unobserved confounder H over here on the right. So I should also say that graphs are designed to represent direct causal relationships, where direct means relative to the other variables that I have. So this is convention that we always include confounding variables. And this approach goes back, just as the potential outcome approach goes back to Neyman in the 1920s, if not Hume. This approach goes back to path diagrams that Stuhl Wright introduced in the 1920s. And as I said, I've told you this before, if I have a directed edge, I'll say X is a parent of Y and Y is a child of X. Okay, so the reason I said that although it's suggestive, there's nothing yet causal about it, is that if I have a joint distribution that factors according to this graph, right, all that's saying is I can write the joint distribution as P of X, P of Y given X. Any joint distribution can be written in that way. I haven't made any assumption, assuming this is well defined. Okay, and likewise, I could also take any distribution, I could factor it according to a graph pointing in the other direction. Okay, so there's nothing, I can't be making any, in the absence of doing anything more, I'm obviously not making any causal assertion here, if it's the case that whatever data you give me, I can always factor it in both of these ways. So this is just a graphical way of the statement that we have in introductory statistics, of course, is that correlation is not causation. So so simply the factorization on its own is not saying anything causal. So how do we get something causal out of the graph? The way that we get something causal out of the graph that allows us to distinguish between this and this is that we say that the particular form of the factorization that we're writing down is special in the sense that we're going to claim that if there's no confounding, the conditional distribution for Y given X corresponds to the distribution over Y that we would get if we were to intervene on X. Or going back to our potential outcome notation, we could write it in this way. Okay? So the causal claim is that if I write down this graph and I interpret it causally, then I'm claiming that this piece of the factorization, Y given X, has this causal interpretation that it's equal to the distribution that we would observe over Y if we were to do an experiment or in which we force everyone to get a specific value of X. or equivalently, the randomized experiment where we pull out a group of people and we randomly assign them to a specific value of x. Okay, so the question is, how does this relate to the counterfactual approach? So I've already started relating it over here. But you'll remember in the counterfactual approach, we said that the absence of confounding corresponded to these two independencies. And if we didn't have those two independencies, then we said there was some confounding. So if at least one of them failed, we said there's some confounding going on. So you might be thinking at this point, okay, so these graphs, the great thing about these graphs is we can read off conditional independence from the graphs. And the counterfactual approach was all about independence. It was about saying that the absence of confounding corresponded to these independencies. The presence of confounding corresponded to at least one of them failing. So there's got to be a connection here, right? I've got a graph. The graphs are supposed to be saying something causal. We've got a language, a potential outcome language for talking about causal models, and under that language, when I talk about no confounding, I say this. Under the graphical approach, when I talk about no confounding, I draw this graph, implicitly leaving out the h. So what's the connection here? Ideally, you would like to be able to look at this graph and read off these independencies. Right? But there's a sort of fundamental problem with doing that, which is it doesn't matter how long you stare at this graph up here, it doesn't have any counterfactual variables on it. Right? There are no counterfactual variables on that graph. So it doesn't matter how long you stare at it, you're never going to be able to directly read off these independencies. And so this has been part of a critique. So for example, Rubin, so the potential outcome model that I showed you is originating with Neyman, is often called the Rubin causal model because he was, Don Rubin was, wrote a seminal paper on it in the 1970s and sort of advocated for the model in a big way. He often has critiqued the graphical approach. How can these graphs be saying anything about causation? There are no counterfactuals on the graph. So this is the solution. This is the simple unification of these two approaches that I'm going to describe. So the idea is that if you give me this graph here, and then you say, I would like to understand what are the assertions. When I interpret this causally, what are the assertions that this graph is making about counterfactuals? I'm going to do this operation where I split the variable x. Okay, and I'm going to split it into two pieces, a random piece, x, and a fixed piece, which I will depict in red. And then everything that goes downstream from that will now get labeled as y of x equals 0. And now if you were to then look at this graph here, so I've split this simply to remind us that it came from there. Okay? But you can think of this as fixed, but just think about this as just a completely ordinary random node in a graphical model. Even if you didn't remember the full definition of d-separation, you can see, well, there are no pathways between x and this guy, so probably that model is telling me that x is independent of y of x equals 0. Right? I've got no pathways, so I can read off this d-separation. Okay? So now I can directly read from the graph the independence that I couldn't see previously. There's a bit more to it than that. I'm also going to associate with this graph on the right a new factorization. And that factorization will just be the standard factorization you'll get if you viewed this as a graphical model, which is, well, here are two variables. Neither of them, I'm thinking of this as fixed now, so neither of them have any parents. So I'll just write it as the marginal for this, and then the marginal for this, marginal over y of x equals 0. But now, this is a new graph that I constructed, and I've got to come up with a way to relate the distribution over these two variables here, x and y of x equals 0, to my original observed variables. And the obvious way to do that is I say that this piece here has to come from y given x in the original distribution, just plugging in x equals 0. Okay, so the basic idea is that I'm going to split this node x, and then the pieces of my new factorization will be inherited from the pieces of the original factorization, just with this condition that when I have a variable like, whenever an x shows up as a parent, we'll fix it to, we'll condition on x equals 0. So basically, the factorization is just a requirement that after I do this node splitting, I can rewrite the joint distribution over these new variables as if it was an ordinary graphical model, so factorizing into each variable given its parents in the new graph. And there's a modularity condition which says that the distribution associated with the node after I do the splitting is obtained from the corresponding term in the factorization before I do the splitting, just plugging in the value of x that we've imposed. Okay. So that's the basic idea in the simplest case. Here I was fixing x equals 0, but I could also do it with x equals 1. Okay, so, or if x took lots of values, I could construct a graph here for every particular value of x that I might want to, every value that the treatment takes. But if it's binary, there are just two values. Okay. So now, if I do it with x equals 1, I get these two nodes, and then I can then read off this independence. And we get a new factorization in exactly the same way as before. Okay, so there's a key point here, which may seem sort of simple, but I'm constructing a graph. I've given you a graph that's got capital X, the random x, and y of x equals 1. And I gave you another graph that had the random x and y of x equals 0. You might think, well, why didn't you just put everything together and construct a graph that has x, this guy, and this guy all together? And there's a important reason for doing that, which is that basically we never get to see both of these. We never get to see both of these. That's the fundamental problem of causal inference, that the joint distribution over both of these is not identified. Okay? Whereas we do get to see, in principle, we can get to see x and y of x equals 0. We can get to see x and y of x equals 1. And in graphical terms, if I had drawn a graph that had all three variables, that had this, and this on it, then as soon as the graph implied this independence and this independence, it would also imply this independence. And if we were to do that, our graph would then be representing joint distributions that are not identified. Okay? And the danger with doing that is that basically the difficulty is that if you try to build a graph where you include all of the counterfactual variables on one graph, very quickly you introduce independence assumptions, counterfactual independence assumptions that could not be tested in any randomized experiment. And this is what, in fact, this is what Pearl has done in his approach. And the result of that is that he ends up identifying quantities that could not be identified by any randomized experiment. So he's building in untestable assumptions into his model, not untestable assumptions in the usual way that we say in statistics. Usually when we have an untestable assumption in statistics, it is the case that, well, we've made some untestable assumption, but if we did a randomized experiment, we could then find out what the answer is. Pearl's approach, which involves putting all of these variables on one graph, leads to make the formulation of models that impose assumptions that could not be tested even in principle by a randomized experiment. So very strongly untestable assumptions. Okay, let me make a couple more points. You might think, well, why did I belabor this whole point of putting x equals 0 and y of x equals 0? The point is that that gets tiring after a while, writing a new graph for every specific value of x. And of course, I could represent everything together as a single graph in this way. But if I do this, I have to think formally this is now a graph-valued function. So this is a template, and you give me a specific value of little x, and then I then generate, this is a little bit like the plates that those of you that have used bugs, there's a concept of plate in bugs. It's similar to this. So the idea is if you plug in a specific value of x, then I get an instance of this graph, but and I can get a different instance for every value of x, but so each instantiation of this graph gives me a model that puts constraints on a different margin, okay, with the red nodes being held as constants. Okay, so here's the intuition behind the node splitting. So the intuition is the following. There's a thought experiment. And I'm not saying this is a real thought experiment you do, but it's the thought experiment that justifies why we make this split. Okay, so the question is, can we think of an experiment where we could identify whether someone would choose to take treatment? Okay, so supposing we're in an observational setting. So people are choosing, or their doctors are choosing to give them treatment. They're not necessarily being randomized. And at the same time, we want to find out what happens to such a person if they don't take treatment. Right? That seems impossible. Right? So we want to find out whether someone would, under natural circumstances, choose treatment. But we also want to find out what would happen to them if they didn't get treatment. Because it seems as if, how could we do that? Because as soon as we discover that they would choose treatment, then they've taken treatment, and then we couldn't find out what would have happened to them if we prevented them from taking treatment. So so Jamie Robbins is an MD, and so he came up with, this is a sort of thought experiment he came up with that would allow us to see both of these things. So consider an experiment where whenever a patient is observed to swallow the drug, so we see that they have x equals 1, we instantly intervene and we administer a safe emetic that causes the pill to be regurgitated before any drug can enter the bloodstream. Okay? So then we get to see that they swallowed the pill, so we know that definitely they're somebody that would choose to take treatment, but then at the next second we then intervene to prevent the drug actually having any causal consequences. Okay? So this is a thought experiment. It's not that you would actually do this, but this is to describe, and we're supposing the emetic has no side effects, so we then get to see subsequently what happens to the patient, and that's their y of x equals 0. Okay, so this is the intuition behind the step from here to here. Okay, it describes it as sort of hypothetical intervention where I get to see x, and then I also get to see y of x equals 0. Okay, I mean there are studies that people do where, for example, where people will say, if there's a treatment that is limited in quantity, people will sign up saying, I would like to receive this treatment, say I would like to get a school voucher, or I'd like to get some kind of treatment, but then too many people volunteer to get the treatment, and so then a subgroup is picked randomly to then actually receive the treatment. And so that is a setting where the people who wanted to get the treatment, but then were randomly assigned to not receive the treatment, would correspond to an instance like this. Okay, so here are some other models to just show you the use of this framework. So here's the instrumental variable model. So how many of you have heard of instrumental variables? Okay, so instrumental variable model, the idea is that we're interested in the effect of x on y, but for whatever reason we were unable to do a randomized experiment where we randomly assigned x. But we have some other variable z that was randomly assigned, and we suppose two things. We suppose that z has some influence on x, and then secondly, we suppose that we make an exclusion restriction that z has no effect on y except through x. So one context of this would be, say, a randomized trial with non-compliance, where we randomize people to treatment versus control, but then people can refuse to comply, in which case the treatment they receive may be different from the one that they were assigned to originally. Okay, so now if I apply this node splitting procedure, I split on z and I split on x, and then everything downstream from z gets labeled with z, everything downstream from x gets labeled with x. And then I can read off from the graph these two independencies, that z is independent of x of z and y of x. So I'll come to that in a second. We do all splits and then we propagate. Yes, that's a good question. It would matter otherwise, but in the way that it's set up, the formal construction, I haven't given you a formal definition of construction, but the formal definition is split everything and then propagate. So here's a harder inferential problem. This is one that's in Pearl's book. in the chapter 11. So supposing I take this graph and we say, well, does this causal graph imply this independence? Okay. So again, even if you're familiar with graphs and familiar with reading off deseparation and familiar with the causal interpretation, it's not at all easy to see whether or not this holds. Perl does have a procedure for doing this, and I'll briefly comment on that in a moment. So here we just do our node splitting. So we split on x0, we split on x1, and propagate things forwards. And then we can see, if you're familiar with deseparation, you can look at this and say, OK, so is this guy independent of this, conditional on this, and this? And you can see, if you understand deseparation, you can see, yes, obviously this does hold, because the only path from here to here goes through here. And if I'm conditioning on this, then that path is blocked. So these two are deseparated given this and this, so we get this independence. Question? Because the query that I had was not asking about Z counterfactuals. Okay. If you had been asking, yes, so you could have asked that. You could have said, you might have asked a query that involved also splitting on Z, but we're not doing that. This is the query that we're asking. Okay. So I'll come back and talk about this example a little bit subsequently. So here's the general procedure. The general procedure is that if I've got a set of variables that are my treatments that I want to intervene on, I take my original graph, I then cut all of them, all of the nodes that are the treatments that I'm interested in this way. The random half, the black half, inherits all of the edges directed in. The red half inherits all the edges pointed out. And then I just propagate downwards. So this is a little bit busy, but basically it's just trying to tell you that after having done all your splits, you let A seep downwards like this, and so everything downstream gets labeled with A. And then the point is that then I instantiate this. I get an instantiation by putting in specific value for my red nodes. Okay, this is just formally stating. This is also a bit busy, but this is formally stating the fact that the conditional distribution associated with a node after we do the splitting is just inherited from the distribution before we did the splitting, just plugging in specific value for each parent to the value that we've intervened on, which is, if you're familiar with the Perl's do calculus or the truncated factorization, is very similar to that. Okay. So then the question is, how could I apply deseparation to this graph? And again, the basic idea is, if I want to test this independence, then I just go to my graph and check deseparation of the corresponding sets of variables. But I also have to condition on any red nodes. So any of the red nodes, those are just taking constant values, so I also have to think of those as being conditioned on. So yeah, let's do some more examples. So here's a mediation graph. So I've got Z, X, and Y, and remember the graph is implicitly supposes there's no confounding. So if I intervene on Z, I then get this graph over here on the right. Factorization just says that the joint distribution over Z, X of Z, and Y of Z factorizes just as you would imagine if this were an ordinary graph. So we get Z, X of Z, because X of Z has no random parents, and Y of Z given X of Z. And then the modularity just relates the Meisner distributions of, relates the conditional distributions of these pieces back to the original graph over here. So P of X of Z equals X is got from X given Z over here, just plugging in our chosen value of Z. And likewise, the distribution for Y of Z given X of Z is just obtained from the distribution for Y given X and Z, plugging in our chosen value for Z here. Okay. And then we could apply deseparation to this to see, for example, that Z is independent of X of Z and Y of Z. Okay. So here's a graph for no direct effect, where we intervene on z and x. And this is the factorization that we get, everything completely independent. This is relating the distribution over here back to the original distribution, and deseparation gives us that everything's mutually independent. Yes, yes, exactly. That's right. So this is so if everything in your original graph was observed, then the joint distribution after the transformation is also identified. So that's a key point. That basically, if we didn't have any hidden variables over here on the left, then the distribution over counterfactuals that the new graph has is always identified, and it's the simple function of the original distribution. Okay, that's the reason. That's explicitly the reason for not putting, say, y of x equals 0 and y of x equals 1 in the same graph, because if you do that, then your graph is representing a joint distribution that is not identified from the observed data. Okay, so here, going back to this inferential problem, and so this is also sort of a claim that the calculus sort of is easier to use. That Pearl, and this is in the second edition of his book, he claims that this graph over here does not imply independence. And we can just read off from this SWIG, and with 2 lines of logic, we can read off that this conclusion is wrong. And the reason we can read it off is that we already inferred this. This was the example that we did from here. And then we can then see if we condition on x equals x0, then x1 of x0 condition on x0 equals x0, just by the consistency logic, the usual logic of potential outcomes, is then equal to x1. Condition on x0 being equal to little x0, then x1 of x0 is the same as x1. So in 2 lines from this, we've inferred that this counterfactual independence holds. So this isn't just a typo, because Pearl uses the fact that he thinks this independence doesn't hold to claim that a claim of Robbins, my co-author, is false. It's actually slightly funnier than that, because it's not just a claim of Robbins, it's a claim that Pearl and Robbins together made in a joint paper, and he claims that claim is incorrect. And of course, this shows that in fact that's not the case. So in his earlier incarnation, Pearl was correct, in the later incarnation, incorrect. But the reason I bring this up is not just to point out that Pearl made an error, but it's that reasoning with these counterfactuals with these graphs is actually difficult, because without having this node splitting transformation. Okay, so this is the way that Pearl would attack the same problem. So he would start off with this graph over here. Okay, so this is just the same as this graph, just rotated. It's the same graph, just turned. He would make two different copies of the graph, like this. One where he's with the counterfactuals on, one without the counterfactuals on, and he would put error terms, these U variables, connecting the variables in these 2 different. This is called a twin network, twin world network, because we have one copy of the graph here and another copy of the graph over here. And if you read his book, he then looks at this graph and says he concludes that this independence does not hold based on this graph. And the reason that he thinks that is because he says, well, I can get from y of x0, x1. So I'm conditioning on z, this guy, and I'm conditioning on x0, these 2. So I'm conditioning on those 2. He says condition on those 2. It doesn't matter. I've still got a path that goes from here up to here, 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 down to here. So therefore, these 2 are deconnected. So in general, this counterfactual independence doesn't hold. But in fact, what's going on is that there are deterministic relationships amongst the variables in this graph that are not captured by his semantics. Okay? Because, for example, if x0 is equal to the same value as x0 over here, then this variable is equal to the same value as this variable over here. And so what goes wrong is that when x0 equals little x0, then z takes the same value as this, which means that when I condition on x0 being equal to little x0 and z, that's equivalent to conditioning on this guy, which then blocks that pathway. So the problem is that there are extra relationships between the variables in the graph that are not captured, that are not explicitly captured in the graphical framework. With Spitzer and Pearl, they have a sort of bug fix for this, whereby they do a pre-processing step on the graph in order to avoid this particular problem. But in spite of that, Pearl didn't apply this bug fix when he analyzed this problem in his book. And the pre-processing step involves some work, basically. OK, let me see. So let me just do, let's just go back to a simpler example. Let me talk about confounding a little bit. So here's a simple setting where I've got x and y and a confounder h. We can read directly from this graph that if we have such a confounder h, then x will not be independent of y of x, right? Because we've got a path going through h. Okay, so we'll work out that this doesn't hold, and so we'll conclude that that we're not going to have this independence. So in general, we won't be able to identify the causal effects on y. This is the same graph, but now in the optimistic setting where we're supposing that that we measured this variable and there are no other confounders. Right? So now, if I go over here, we can see that yes, x and y of x are not nicely independent, but they are independent given L. So there's only one path between these two, and it's blocked by L. So it follows from that so this in the sort of Rubin framework, this would be called conditional ignorability. So it follows from that, it's about 2 lines using factorization and modularity to show that then we can get the distribution in y of x by just applying this formula, which is called the backdoor formula. So we can get it from y given L and x times P of L minusizing over L. Okay, so here's the proof of that. So this is what we're interested in. We go to our graph over here. We say, OK, exactly as you were saying, well, that's identified by taking y of x equals y given L and P of L. That's what this graph tells us, that this is the joint distribution over y of x and L. And then by independence, I can put x in there, and then I can then get from here to here by modularity, and I've then shown that I've shown that this distribution that I was interested in is identified. So okay, so this extends to thinking about situations with. I won't have time to go into all of this, but the kind of situation that Jamie Robbins has sort of focused on is a situation with multiple treatments. So where, say, A is the first treatment, B is your response to the first treatment, C is then a second treatment. The first treatment is randomized. The second treatment is randomized, conditional on whether or not you receive the first treatment and your response to that first treatment. And then what you want to know is something like, so for example, the kind of study where this is done is where C, say for ethical reasons, C could not be assigned completely randomized, but it had to be assigned, say, randomly conditional on your response to the first treatment. So say this might be something that helps you with side effects that you get from the first treatment. And so what you would like to do is you'd like to know the result of intervening on both A and C, because the kind of situation you would worry about is a situation where, say, the first drug is really useless, but it does make you suffer nasty side effects. Those nasty side effects mean that you're more likely to be given the drug to help you with the side effects, or maybe that drug to help with the side effects helps you with the thing that the original drug was given for, so that even though A has no effect on D, the final outcome, it has an effect through this process of making you suffer bad side effects that then make people give you the good stuff. And if you were one of the patients, you would say, couldn't we cut out the whole bit in between where I first had to have the nasty side effect in order to then be given the good stuff? Okay. So results of Robbins show that basically give counterfactual independence conditions that then allow us to identify the effect of A and C on D via this formula that is called Robbins calls the G formula. And so again, there are these results in the statistical literature that give these counterfactual independence conditions, and then say that if these counterfactual independence conditions hold, then we can then apply this formula to identify this intervention distribution. So the question is, does it hold? Well, again, we can just split on A and then split on C, and then read off from the graph. Okay, does this hold? Well, is there any path from A to D of AC? No, there isn't. Is there a path from C of A to D of AC conditional on B of A and A? And we can see that, again, we could check that and see that, no, there's no path from here to here. We have to keep in mind that we're also conditioning on this red guy, but there's no path from here to here conditional on this, this, and this. Okay? So that would then allow us to see that we can apply this formula to identify the effect of A and C on D. So just to contrast this, this is the graph that answers this question to check these two conditions in the way that we formulated it. In order to do it with the twin network approach, you have to build 3 copies of the graph, connect them via these error terms, and then check the independences on this particular graph. Okay, so the basic point is we can then consider other settings. So here's a setting where, say, we have a first treatment, we have a response, we have a third treatment. But now, whereas in the previous setting, A was randomized, now we have a confounder between A and B, but that confounder does not feed into D, and also does not feed into C. So intuitively, you might think, well, could I apply the same formula that we did in the previous setting? And again, we just split. We can read off from this graph that the same independence, these two counterfactual independences, also hold in this graph, and thereby see that the same identification formula holds in this quite different context from the one that we saw. Okay, so you can see I'm running out of time, so I will end and summarize here. So I presented a simple approach to unifying graphs and counterfactuals via node splitting. This works by linking the factorization associated with the two graphs, provides a language that allows counterfactual and graphical people to communicate, I hope, and it leads to many fewer, in fact, we can say precisely super exponentially many fewer untestable independence assumptions than the approach based on non-parametric structural equation models with independent areas that Pearl has advocated. And I haven't talked about it here, but it also provides a way to combine information on the absence of individual and population level direct effects. And that's it.